Okay, good afternoon, everyone. So wanted to start by just letting you know that on Thursday, November 11th, most likely I'm going to be out of town for a surgical procedure for my wife. And so I'm not sure how I'm going to handle that yet. There's pretty much like two options. I can have a sub come in and do a Zoom class, which would be interesting. Or the other thing I could do is go look at my like over I think I have over like 1,500 videos of lectures and go, pick one of the ones that will cover the material that we're going to cover that day. I doubt we'll be at this point. I don't know yet, but I could just say, hey, everyone, watch this video, and then we'll just come back on that Tuesday afterward. And if you have questions, I can answer questions. So those are kind of the two different ways we can go about it. Think about what you would prefer, and then we'll do a poll maybe next week, just to kind of, that way we can plan ahead. Everyone will know what's going on. Just want to let you know about that. Okay, any questions over chain rule, the homework?
Not really.
How was it?
Worked pretty all right. There was that one problem, like the third to last one, where we had to take the second derivative of one.
Okay.
And it was awful.
Yeah.
It all made sense, but there was just so much of it on that second one that was so bad.
Yeah. Okay.
That's all I have to say.
Okay.
That one was just comedically hard to do.
Yeah. If you got through this homework and you understand, what's going on here, like you're in good shape. If you're not, and you're not speaking up, you need to ask questions.
I'm still working on it.
Still working on it?
Yes, sir.
How far into it are you? Just out of curiosity.
22.
22. Okay, so you're getting there. There's still, yeah. So 22, that's when you first start hitting kind of these weird combinations of chain rule with quotient rule, or you'll have a product rule with quotient rule. So you start to get some really strange varieties after you get past 22. So see how it goes for you. All right, well, if there's no questions, I'm going to proceed. Okay, if you could get ready for a quiz. We're going to do something different today. So I'm going to give you a quiz. It's 3 questions. It's multiple choice. It's chain rule. And you'll be using the poll to put your answers in. I'm going to give you 8 minutes to do 3 problems. You all ready? There they are. So it's problem number 1 is y equals this, and then here are your options for its derivatives. Here and here. Hopefully you can see that. I can try and make it a little bit bigger for you. There you go. And then the poll should pop up here. So I've launched the poll. So you're going to just answer, A, B, C, D, or E for each one. And 8 minutes. Enjoy. These problems, I would say on difficulty level, 5 being the hardest, 0 being the easiest. These are like 2s and 3s. Twos. So just to be clear, you're taking the equations or functions in yellow and differentiating them and then choosing one of those answers. We're halfway. Okay, we have 1 minute left. Okay, so that's it. Let's see what the results were here. So I think all of you can see that. So it looks like for problem 1, most students picked D, and then B, and then E. Let's see. DBE, that is correct. So let's take a quick look at this. So on the first one, you've got, you know, something being raised to the 3rd power. So you bring the 3 down, you rewrite what's in the box squared. So I did that. And then you take the derivative of what's inside, which is 2x. And then the only thing left is just to multiply the 2x times 3, you get 6x here in front of this. So that's option D. And then on this one's pretty much the same thing. You've got something to the 4th power. So first the 4 comes down, then you rewrite everything here to the 3rd. So I did that. And then I multiply that times the derivative of the inside, which is just 3 minus 4x. And there is one more thing to do here. You can move this out front and then distribute the 4 through. And you get this, which is choice B. And then on the last one, this is a triple composition. So first thing is to realize that this rewritten is this. So you've got, you know, ultimately you've got something being cubed. So you bring the 3 out, you rewrite everything to the 2nd power, then you've done the 3. So then you move inside, you take derivative of sine of something, right? Derivative of sine of something is cosine of it. And so now you're done with the sine, then you move on the inside of that, take derivative of 4x, you get 4. And you can put the 4 together with the 3 to get 12, and then you can slide this. Well, I don't know if they actually slid it. They left it like this. I put my cosine 4x in front of the sine squared. It doesn't matter. It's all multiplication, so it won't matter at the end of the day. So I hope that gives you some idea of what I expect you should be able to do in 8 minutes at this time, at this point. If it took you a little longer, you didn't get through it, then that just means that you need to, you know, get up to speed, so to speak. Because on the test, part of the exam is going to be like how efficient you are. I think I told you this on the first exam too. It's not just can you do it, it's can you do it within a reasonable amount of time. So, okay, any questions on this? Do y'all like these quizzes? We can do these every day if y'all want. Some people want them, some people don't.
I don't mind them.
It's
but-
cool. Go ahead, bro.
Oh, I just said I don't mind them. That's all.
I don't like them because we don't have 15 minutes for me to throw away every class, you know, like, but I want to, this is one section where I want to make sure I'm keeping everyone honest. Like you need to make sure you're doing this homework and that you're ready for the next step. All right, so here we
Question.
go. We're
How
moving
much,
on.
how much does getting one of those wrong hurt us? Because I got the second one wrong because I I didn't see that they distributed that 4 through, and so I answered it A because I misread what was going on.
Yeah.
Like-
I don't know. Let me see. Let me just put all the grades together and I'll see, where the class is. I mean, technically it's a third, right? So if you miss
Yeah,
one,
that's the thing, because
I'm gonna pass.
that's an F.
Well,
Or
it
almost
would
an
be a
F.
D. It would be a D, but
Oh, that's still really bad.
we'll see. We'll see. Okay, so today we've got the next section is, the chain rule, I think itself is difficult for students because there's so much in the little nuances of things. I told you last time to do today's stuff, you got to be comfortable with chain rule. You don't have to be like a master at it, but you've got to be comfortable with it. So there's a few things that I have to actually put in place before we can get into the section. Some things are going to seem a little strange, but it's going to be very important that we understand to begin this thing. So first things first. All right, so when we were talking about notation, right? When we first started talking about derivatives, I said, if y is some function of x, then if I want the derivative, I just write y prime, right? I put y prime, meant for us to find the derivative, right? And it was a nice, clean, easy way of me telling you to go get the derivative. Now, there were other notations. There was another notation, Leibniz notation, that said, instead of writing this, write dy dx. And we actually saw how you could use that notation in the chain rule to kind of help understand what's happening in the chain rule, but it's just a different notation. So, but this is going to be the preferred notation for the next two sections, and here's why. In this Leibniz notation, you can identify this variable x. This variable x is, back in college algebra, what we refer to as our independent variable. And then the numerator variable, that refers to this, which is the dependent variable. So in other words, if you have an equation where you have solved for y, then y is a function of x, right? Y can be determined. You give me x, if somebody gives me x, I can tell you what y is. So the x is independent. Anyone can hand me whatever x value they want. The y depends on that x, right? So when we write our notation this way, this still means take the derivative, but we can add a little bit more to this. We're basically saying, this notation basically says, what is the rate of change in y with respect to x. It's how much does the y value change on a function if you change the x a little bit. We talked about this last class. I drew a picture. I said, what we're ultimately doing with the slope of the tangent line is we're saying, hey, look, what's that slope, m? If you change the x a little bit, how much does the y go up? And that's your slope, that's your derivative, right? So this notation just kind of lays it out there right in front of you. You can tell from that notation that the y depends on the x. The numerator variable depends on the denominator variable. You with me? Another way to write this using Leibniz notation, another option would be for me to write it this way. Take the derivative with respect to x of y. These are equal. In other words, they mean exactly the same thing. So this is really saying, how much does y change if I change x a little bit? So I'm taking the derivative with respect to x of y, but it means exactly the same thing. Again, the advantage to this notation is that you can tell what the independent variable is. You can tell what the dependent variable is from this notation. If you just write y prime, what's missing? What's not here?
Dx.
X.
You don't have an x, right? And you may think, oh, well, that's no big deal. I just assume that it's x. Well, let me show you why this becomes important, all right? So what if I have this? What if I say, take the derivative with respect to x of the number 7? What would your answer be? So I'm asking you to take derivative with respect to x of a constant. What's the derivative of every constant?
0.
0. Okay, so this is 0, right? Okay, great. All right, what is the derivative with respect to x of just x itself?
1.
1. Now look at that. If I rewrite this using Leibniz notation, it's really saying dx, isn't it? It's like this notation right here. You slide the y up on top like this, and you're back to this notation. So if I write, take the derivative with respect to x of x, you can rewrite it as dx over dx, and I hope that that's clear to everyone that that's 1, right? Anything over itself is 1. So that matches with what we know, right? The derivative of a constant is 0. The derivative of x is 1, right? Okay. So now let me ask you, what would the derivative with respect to y be of 7? Well, that's still a constant, right? And the derivative of a constant is always what? 0, right?
0.
0, right? But if I ask you, what is the derivative with respect to y of x? What's your answer? Well, it's not dx over dx anymore, right? It's dx over dy. And quite frankly, I don't know what that is. I can't tell you how much x is changing with respect to y because nobody's given me a function here. Like I don't have an equation to work with. But the point is that the derivative of x here with respect to x is 1. We know that. The derivative of x with respect to itself is 1. But the derivative of x with respect to y is not 1. It's the rate of change of x with respect to y, which is whatever it is, okay? So we have to be very careful about what we've learned in the past. We've been very, very loose with our notation and our understanding of things because it wasn't a necessity early on to make these little things, I guess. We didn't want to point this out early because it would have confused you even more. So we just kind of like cranked away. And then now we're here at a point where we need to start really thinking about what we mean when we say take the derivative with respect to x versus with respect to y. Let me see if you're understanding this. What would the derivative with respect to t be of t squared?
Be 2t.
2t. That's just like me asking you what's the derivative of x squared with respect to x, which would just be what you normally think it is. This is just 2t. But if I ask you what the derivative with respect to x is of t squared, well, what's that, right? Because we don't have this variable and this variable are not the same thing. Do you all see that? Here, they're the same, so I can just treat it like I've been doing the whole time we've been doing derivatives. Here I can't. Okay, so this is a big question mark right now. How would we deal with that? And I'm not going to answer the question yet. Not going to answer the question yet. I just want you to notice that it matters. Okay, it matters what the variables are.
So question.
Yeah.
This, I guess in this like where you're taking the derivative with respect to a number and then you don't know the formula.
Mhm. Well, I would never do that. You would need to know the formula. You would need to know the equation you're working with in order for you to ever answer that question.
Okay, gotcha. I was going to
Yeah.
say, is there some trick to this, or is it?
No, this right now, I
Okay.
just don't know. All I want you to see is that the y prime notation isn't good enough. All right.
Yeah.
Once you start getting into more complicated equations that involve more than just x and y, then you need to be very specific what it is that you're taking the derivative with respect to. Here it was assumed, see this, by writing y prime, there is an assumption here that y depends on x,
Yeah.
right? There's an assumption of that.
Yeah.
But that's the drawback to that notation. So we have another notation which means the exact same thing, but it very clearly states in the notation what is
Which one is dependent and which is independent.
exactly, which
So,
is dependent and which isn't.
so if you had a given formula, y equals x plus 1, your dy dx of that, it would just be you're solving it normally. But if you flip that over and had a
Let's
dx
do it.
dy,
Let me do it.
yeah,
Let me do it right here. Watch. Let's say we have y equals x plus 1. And I ask you for y prime. All right. Everyone here should be 1. The answer is 1, right? There's nothing is going to change from what you
Yeah.
already know. Okay, that's the good news. Okay. The derivative of this should be 1. But if we look at it a slightly different way and we say instead of this notation, if we're asking for dy dx, the way I'm going to have you now look at this is that you're going to take the derivative with respect to x on both sides of the equation. Okay, this is the new thing today, and I'm getting a little ahead of myself, but it's okay. So what I'm doing is I'm saying, hey, look, I want you to differentiate both sides of the equation with respect to x. Now I'm doing it with respect to x because this is what I asked you to find. Or I didn't technically say it, but I'm going to say it now. Find this, okay? Find dy dx. So when you see dy dx, you say to yourself, okay, I want to differentiate with respect to x. So I'm going to do that on both sides of the equation. On the left side, what is the derivative with respect to x of y? Well, we don't know what that is, right? Because those are two different variables. So I'm just going to write dy dx. That's the left side of the equation. The right side of the equation, I have two terms here, right? X and 1 added together. I can break this up and do the derivative with respect to x of both of them. Okay, so I'm taking derivative of this one with respect to x and this one with respect to x. So dy dx equals, okay, derivative of x with respect to x is what?
1,
1. And then the derivative of a constant is
0.
0. And so look what you have here at the end. Dy dx is 1, which is what we said it was going to be in the very beginning. Okay. It's just a different approach, and you'll see why it's important in a moment. You'll see why this is important. But it's the big change here is that instead of just having something solved for y, and then when I ask you for the derivative, you're just focusing all your attention on this and just using the rules. You're now differentiating both sides of the equation with respect to x and just seeing what happens on each side. I'll do more examples, obviously, I'm going to have to, but
So
go ahead.
So just one question with, say, this formula in particular, and maybe this is me trying to extrapolate things in a very wrong direction. So just tell me if that's the case. Would you be able to find dx dy of this?
Yes.
That inverted, would that be solve the equation for y and then do it?
Yeah, so if I took y equals x plus 1, and I asked you to find dx dy instead, then you're going to take the derivative with respect to y on both sides. So you're going to do the derivative with respect to y on the left, and the derivative with respect to y on the right side. Now on the left, what would the derivative with respect to y be of y?
1.
1, because that's dy dy, right? So that's 1 equals, now you have to do these separately. Derivative with respect to y of x plus the derivative with respect to y of 1. The derivative with respect to y of x is actually what we're looking for, isn't it? That's dx dy. And the derivative of a constant is always 0. So your answer here would be 1 equals dx dy. It happens to be the same answer. It's not always the same answer,
Of
but it
course.
happens to be because it's a linear and it's very nice. It works out to be the same. But now, does that make sense to you? I asked, the first question was, again, here's an equation relating two variables together, x and y. And I'm asking you, how much does y change if you change x just a little bit? And the answer is, it'll change at a rate of 1. And it's because it's a line, right? If we graph it, it just looks like this. But so a little change in x, the y will go up by the same amount. The ratio is 1, the slope is 1. The second question says, hey, if I change x a little bit, if I change y a little bit, so if I change the up and down, how much will the left and right go? And the answer is the same. Because again, it's a line. Understand? Now here, let me throw the wrench into this. Let's take the same equation. And let me ask you for dy dr. What? Right? You look at it, you're like, what are you talking about? Dr. Right?
Yeah, what
I don't
the
see
hell
an
is
R
that?
anywhere, right? There is no R anywhere. That's okay. Watch. I can still do it. I'm going to take the derivative with respect to R on the left, and then the derivative with respect to R on the right. Okay. Now, what on the left, what is dy dr?
You can't find that. It would-
Don't know, right?
It would just be
dy
dydr.
That's what it is. It's the rate that y changes. If you change r a little bit, it's the rate that y changes. I don't know what it is yet, but let's just keep going. On the right-hand side, let me see if you can, I'll do it slowly. ddr of x plus ddr of 1. And so the first one there is dx dr, right? Because I don't know what this is. It's the rate that x changes if I change r a little bit. I don't know what it is. And then this right here, I do know is 0, so plus 0. So I was trying to find dy dr, right? Well, guess what? dy dr is equal to dx dr, but I don't know what dx dr is. But that's the relationship I have. Again, we're getting a little ahead of ourselves, but I think this illustrates that when you take the derivative of an equation, it really doesn't matter what you do it with respect to. I mean, you could do it with respect to x or y or r, anything you want, okay? The operation of taking the derivative is that you take the derivative on both sides of the equation, you just see what happens. If it's not sinking in, it's okay. We're gonna have more time today to understand this. Okay, so the next thing I want to point out to you, all right, and this always just causes a little bit of trouble for people. All right, let's act like we haven't talked about anything at this point, right? If I would have walked into class today and say, here's a quiz for everyone. Y is equal to x to the 4th. Find y prime, all right? Find y prime. Everyone here is going to say 4x cubed, right? I agree. Okay, that's correct. But when you're doing that, when you do the 4x cubed, you're not using chain rule, right? You're using power rule. You're just using the power rule. Okay, I want you to look at it like a chain rule, because it actually is a chain rule. Watch. When I take the derivative of this, I want you to visualize that this is actually like a box being raised to the 4th power. So let's do the chain rule, right? The 4 comes down, and then you have the box to what power?
The third.
Third, okay? The chain rule says now take the derivative, right? Multiply and take the derivative of what's in here. So I'm supposed to now take the derivative of a what?
X, which is 1.
X, which is just 1. And then of course this box was x. And so you get the answer that we expect, right? We get what we expected. 4x cubed times 1. That 1, we've never really thought about that 1 being there, have we? But it's been there the whole time. Now, I want to do the same problem again, okay? I want to do y equals x to the fourth. And I want you to find dy dx. So I'm asking you the same question. Your answer should be 4x cubed, all right? But it's the way we're going to do it that's going to be different. So now what I'm going to do is I'm going to take the derivative with respect to x on the left, and I'm going to take the derivative with respect to x on the right. Yes? The left side is dy dx. The right side, I want you to think chain rule, okay? You're doing that red box to the fourth, right? So first the 4 comes down. Then you have the red box, which is x, to the third, right? Times what? I know you want to say 1, but you're really taking the derivative of what?
X,
With respect to,
X.
so you just said you're taking the derivative of x with respect to x. That's what you said right there. You're doing right there.
Yeah,
Okay, yeah, and that's a 1.
Yeah.
I agree. I need everyone to see that though. So you're taking derivative of x to the fourth, the 4 comes out, x cubed, times the derivative of x with respect to x, which is dx dx, which is 1. So everything comes out as expected. All right. Let's see if you really understand that or not. We'll leave that up there. Here's what I'd like for you to do. I'd like for you to take the derivative now with respect to x of y to the fourth. Not x to the fourth, y to the fourth. Think chain rule. We have this green box to the fourth. How do we take the derivative of a green box to the fourth? 4, right? 4. Green box, what's our green box?
Y.
Y,
Y, and then to the
third.
third. Now, critical step, critical step, times. Now you get to go to the box and take the derivative of it. What's the derivative of y with respect to x?
dy dx.
Dy dx. Is that 1?
No,
No,
well, not necessarily.
it's not necessarily 1. It's dy dx. And that's your answer. The derivative with respect to x of y to the fourth is 4y cubed times dy dx. The derivative of x to the fourth, right? The derivative of x to the fourth with respect to x is 4x cubed. The reason it's 4x cubed is because that dx dx is a 1. Here, the reason it's not just 4y cubed is because the variable here and here don't match. And so that little d whatever that comes out after chain rule is going to be not 1, okay? Let me do another one. Let's see if this is really sinking in or not. What would the derivative with respect to x of sine of y be? So do you all see chain rule here? You have sine of a
Yes.
box, right? What is the derivative of sine of a box?
Cosine of
Cosine of a box.
Cosine of it, right? So cosine of y. We're not done though, right? Chain
Yeah.
rule says now we have to go in and take the derivative of what's in here.
Yeah.
So
It'd
what's
be-
the derivative of y with respect to x? dy dx, right? See, this matters, right? This dx matters. What you're differentiating with respect to matters. So derivative of sine of something is cosine of it. times chain rule times the derivative of what's inside, derivative of y with respect to x is going to be dy dx. Very different than this, right? Just to be clear, if I asked you to find the derivative of sine of x with respect to x, then your answer is cosine x. But the reason it's cosine x is still chain rule. Derivative of cosine of sine of something is cosine of it. Then you take the derivative of x with respect to x, dx dx, but that's a 1. So this just turns out to be your good old fashioned cosine x. So I'm gonna give you one more. This is a famous problem. There's a story behind this one, okay? What is that? It's not a tricky problem, and it's something we've already talked about, but what would that be? Is it 1? It's not 1, right? It's dx dy, right? That's it. Dx dy, that's all it is. I don't know what that is,
Yeah.
but it's not 1, okay? So this is a story. I always share this with my calculus classes when we get to this section. So when I was in graduate school, if any of you ever do graduate school, at least my experience was that all I did was I lived at the library. I slept on benches and stuff. Like I would literally be like on the campus for like 3 days without going home. Maybe it was because I did math, I'm not sure, but I just like lived, breathed, everything. My whole life was math, right? So that's not healthy at some point, you know, you have to have some outlets, you know? So I would like once a month, maybe once every 3 weeks, I would get together with my buddies and we would go out, right? So I had this routine. There was this club that we would go to. They played like really like crazy house music and stuff. And we would just like go there. And at the time I was 21, so I was able to drink. So I would just go and just let it go, you know, just let it go and have a great time, go dance and sweat and just get all this kind of frustration out. Anyways, you know, you're out there and mingling around, you meet people, right? So I would meet girls, and I always had this thing in my mind where I knew that I had no time for anybody, right? So, I mean, just to be fair to any person I met, any girl, I'd be like, you know, you're wasting your time here. I don't have time for you. I'm sorry, you know? But I always had this like minimum bar question that I'd ask any girl that I started talking to. And I know this sounds really stupid and arrogant, but Angel's agreeing with me. I would always have this, I always figured if I'm ever gonna have like a conversation, they have to know some math, right? Like they're gonna have to know some math for me to be interested in talking. So my minimum question that they had to be able to answer was, what's the derivative of x, right? If they can answer that, at least they've seen some calculus, right? So I'm at the club one night, meet this girl, we're dancing. We danced for like 2 hours before I even talked to her. I go up to the bar, she's up there. She actually came up to me and started talking to me, and I asked her, I said, what's the derivative of x? Her answer was, does anyone want to guess what her answer was?
Did she ask you what it was in relation to?
Yes. She didn't answer 1. She said, with respect to what variable? And I just went, whoa.
Did you marry her?
Here we go. No, I didn't marry her. I didn't marry her. So, so she answered that question with respect to what variable? So that told me, okay, the standard answer I would have expected was 1, because most Cal 1 students are going to say derivative of x is 1. Got that, understood. But really, at the end of the day, the derivative of x does not have to be 1 if you're differentiating with respect to something else, like this problem with respect to y. So it's important to know what that independent variable is. And so that's what she asked me, what's an independent variable? So then I was like, wow. So then I asked her another question, which was not, I wasn't prepared to ask a second question, but I did, I had one because I was already blown away. So I asked her the question, I may have talked to you all about this. If you take all the numbers between 0 and 1, and you close your eyes and reach in and grab a number, what's the probability that it's a fraction? Understand? All the numbers between 0 and 1, close your eyes, reach in, grab a number. What's the probability that you grab the fraction?
Isn't it infinite? Since there's
Infinity?
infinite
It's 100%?
fractions between, yeah.
100%?
Aren't they all
Okay.
fractions?
Aren't they all fractions, right? I mean,
Yeah.
I mean, so like, what do normal people think, right? Actually, the probability is 0. There's 0 probability that you'll grab a fraction. And that's because there are an infinite number of fractions, but there are also an infinite number of irrational numbers that are not fractions. So Daniel, you said, aren't they all fractions? The answer is no. There's actually a bunch of things that aren't fractions. And there's 2 types of infinity. There's countably infinite and uncountably infinite. And the irrational numbers are uncountable. The fractions are countable. Anyways, she knew the answer, right? So that means she knew measure theory, which is something that you studied. So anyways, this girl was super bright. She happened to be there for one night for her friends, something or another. She left the next morning. I exchanged emails with her because this was back in the day. We didn't have the technology we have now. So I think I wrote like her email on a napkin or something. Anyways, I still talk to her every once in a while. We do like 5 to 10 year check-ins with each other to see, hey, how you doing? And she programs robots that weld cars together. So cars will, companies will hire her company to go in there and set up the machinery. They get it all set up and she goes in there and makes sure that all the robots are going to weld everything properly. So anyway, real
What a
smart
baller.
girl. Yeah, real smart girl. Yeah, so I always tell that story because I want everyone to know, like, this is the big thing for today is like differentiation up to now has been with respect to X and it's just been understood. But in the big picture of things, the independent variable matters. It does. And it's going to allow us to now do some things that are going to kind of blow the doors open on what we are allowed to do with finding slopes of tangent lines, as I'm about to illustrate right now. So we're now officially halfway through class, but ready to get into today's notes. So we are now talking about implicit differentiation. Okay, so far, everything we've been doing has been something like this. Y is a function of X. And then when we take our derivatives, everything's just been, power rule, product rule, quotient rule, chain rule. We've got all this. Great, great. Well, everything that we've done, you've been able to solve for Y. You've been able to get Y equals some function of X. But what if you can't? What if you cannot do that? What if you can have an equation, but you cannot solve it for Y easily? Then do we still have the ability to find the equation of the tangent line? So some equations are very difficult. So here are some examples. There's 2 types of equations that we deal with in math, at least functions or equations that have 2 variables. We have what are called explicit equations. Explicit equations mean that you can explicitly solve them for one of the 2 variables. So like this first equation is solved for Y, right? In order to know Y, all you give me is X. Then I'll tell you what Y is. Here, same thing. I can tell you what Y is. All you do is provide me X. Here, if I can provide you what X is, but you have to give me Y. So the X depends on the Y here, but it's solved for X, right? There's no X's over here. Solve for Y. There's no Y's over here. It's solved for Y, right? There's no Y's over here. But look at these equations. Could you take these equations and solve them for X or solve them for Y?
Yeah.
Would it be easy? Well,
No.
I think the first one would be.
Yeah. The second one wouldn't be too hard to solve for Y or X.
Well, let's get to it in a second. How about this one? Can I solve this for, let's say, Y? Can I get Y by itself? Well, I can move the X squared to the other side, right? But
Take
this
the
is the
square root of
point
the whole
that things
thing.
get weird, right? Because when you do the square root on both sides, you have to do plus or minus, like you have to. So now you have plus or minus the square root of 16 minus X squared. So that's actually two different functions. One of them is the plus root and the other one is the minus root. So let me see if we can take this and so I have solved for y, but the plus or minus kind of weird. So let me go to Desmos. I want to graph that for you. Okay, I'm going to graph this. So I'm going to graph y equals the square root of 16 minus x squared. Okay. And then the other one was y equals negative square root of 16 minus x squared. What is that?
That looks like a circle.
That's a circle. Well, look at the original equation. Do you recognize that equation from pre-cal when you were taught, hopefully taught, the general equation of a circle centered at HK? That is the
Yeah, that's
general
mechanics.
formula for a circle that it has a center of HK. So if the center of your circle is 0, 0, this becomes a 0, that becomes a 0. And so you get x squared plus y squared equals r squared. The radius here is the r here is the radius of the circle. So for us, x squared plus y squared is 16, means the radius is 4. Understand?
Yeah, so we just make a circle.
We do. But when we go to solve for y, right? When we go to solve for y, we get two functions, right? Because aren't circles not functions of
Yeah,
x?
they're not functions.
They fail the vertical line test. So the only way to draw it by solving for y is if you draw me two pictures. One draws the top, right? The top by itself, I'm going to clear all this. The top by itself is a function, right? Passes the vertical line test. The bottom by itself is a function. But the two of them together, well, that's not a function, right? But I think it's completely natural. I'm going to type in the equation of the circle here instead. And instead of doing the two functions, I'm just going to get rid of those and have the computer draw me the equation, not solve for x or y. It draws me the circle. And so now there's a very natural question that comes up from this. If calculus is about finding the slope of the tangent line, can I find the slope of the tangent line, let's say here, or let's say here on a circle? Can I or can I not? When we run into a problem, the problem is that, again, a circle is not a function. So remember when we've said in the past, like f prime of x, that means go to x and then go to the function, give me the slope of the tangent line. If I tell you to go to x here, right? If I plug in an x, if I plug an x into this equation, aren't you going to get two y values?
Yeah.
Try plugging any x you want in there, like 0. Plug in 0 and you're going to get plus or minus 4. So when you plug in an x, it's not clear whether or not I'm talking about that value or that value. Do you want the bottom tangent line or do you want the top tangent line? Which of those do you want? So we have a problem here. Do y'all see that? This is an issue. Is there any way that we can get around the idea that this is not a function? And that's what this section is about. Can we get around it? Let's go back to the problems I had. Let's look at that next one. Is there a way to solve this one for y? Can you solve that for y or x? I don't care which one you want to go for. I challenge you that you won't get either one. You want to try x? Okay. Move all your x's to one side, all your y's to the other. Okay, can you get x equals by itself? Just x equals and then something. I could factor an x out, couldn't I? On the left side, like that. And then maybe you're thinking, oh, I can divide through. But what's wrong with that? If I divide through by the x squared minus 1, you know, like divide x squared minus 1 over here, divide x squared minus 1. Now you got x by itself, right? Or
Yeah,
do
but
you?
then you have x on the other side.
Yeah, x is over here. So the only way you can know what x is to know both what y and x is. but you don't know what x is. So how are you gonna know what x is? It's a circular argument. You can't figure out what x is. So that doesn't work. So I leave you to this if you want to waste the rest of your life. You will not do it, okay? It's not gonna happen. Well, there's probably some crazy algebra thing we could do here, but it's way beyond the scope of this class, all right? So I would give up at that point. And then on the other side, you can't do anything either. You can't get y by itself. And equations like this come up all the time, all right, in the real world. And they are called implicit equations, IM, implicit. Explicit is you can get one of the variables by itself in terms of the other variable. Implicit, you can't, all right? Now, does that mean that it doesn't have a graph? Let's see. Let me go to my graph and let me type this in. Let's see what it looks like. I'll leave that there. So if I type in x cubed plus cosine y equals x plus y squared. There it is. First thing I'll point out is it's not a function of x, right? It fails the vertical line test. But it sure as heck has points, right? I mean, there are points on this graph. And if there are points on the graph, then I should be able to go and ask you, hey, go to that point and tell me the slope of the tangent line. Or maybe go to that point and find the slope of the tangent line. The problem, again, we run into is if I tell you to go to this point, let me zoom in on this. If I tell you to go to that point right there and find the slope, oops, hold on. If I tell you to go to this point right here and find the slope of the tangent line, there's an x value that corresponds to that point, but that x value also corresponds to this point. So are you talking about the bottom one or the top one? We again run into this issue where it's not enough to just know the x to find the slope of the tangent line. Say it again. We're running into this problem where it looks like it's not enough to just know x to find the slope of the tangent line. It looks like we're going to have to know both the x and the y in some way. Now, the last equation, I'm just going to graph it because it's a cool graph. You can try all you want. You're never going to solve for x or y over there, okay? It's not happening. Do y'all believe me on that?
Yeah, I'll believe you like that one. I don't, the other one, the second one, I thought at first, and then you started graph like trying to do it, and I was like, oh yeah, no. That one,
yeah.
No, not that one at all.
Yeah, this one's real bad. Oh, that is awesome looking. All right, clear this out. Let's get rid of the other one here. How's that for a graph? So let's say I want to know the slope of a tangent line somewhere on here. Well, if I go to some x value, let's say I pick this x value right here, right? How many different points correspond to that? There's this point. If you go straight up, there's this point, then there's this one, and then you keep going up, there's another one here and another one here, and maybe another one there, and then down, there's one here, down there. So which one of those are you talking about? Because those all look like they have different slopes, right? But I mean, if calculus is worth anything, shouldn't we be able to do it in some way, do this, right? Think about something very simple. Take a piece of paper, go grab a little ant or something from outside, or a little roly-poly, put it on the paper and watch it walk around, okay? And so if it starts walking around, you could sit there and trace out the path and try and find the slopes of tangent lines, which if this were a real problem, that could somehow represent velocity, but that's a different thing. But what you need right now is you need to make sure that little roly-poly stays walking a certain way. You don't want that roly-poly to do this. If that roly-poly does that, as of right today, our calculus falls apart because that's no longer a function of x. But in the real world, we want to be able to have things move around, especially in three-dimensional space. You want things to move around and do what they need to do, and then be able to find instantaneous rates of change. So if we can figure this out, then it opens up the world to us in terms of what we can actually find slopes of tangent lines of. I hope that makes some sense. All right, so I think you're probably just ready to get down to it. So how are we going to do it? This is me basically saying the same thing, that if you have 2 points, if you have 2 points on a circle that correspond to the same x coordinate, you have two different tangent lines. If we take some other function that maybe behaves like this, you have, for the same x coordinate, you have two different tangent lines. So as we can see, we got issues, okay? So we now learn a new type of differentiation. A new type of differentiation. It's called implicit differentiation. That's what this section is about. And really, there are no notes for it. That's it. I now just show you. And the good news is you've already seen some of it. So let's start with the very first problem we had, the circle. Let's take this. Take x squared plus y squared equals 1. And I want you to find y prime. And I'm going to be very specific here. What I mean here is I want you to find dy dx. Okay? Find dy dx. Now, I cannot easily solve for y, right? I can solve for y, but not easily. That's okay, all right? Because now we have this new type of differentiation called implicit differentiation, which just means you look at the independent variable here, dx, and that's what you're going to do to both sides of this equation. You're going to differentiate implicitly with respect to x. So I'm going to take the left side of this equation and take the derivative with respect to x. And then I'm going to take the derivative with respect to x of the right side of the equation. That right there is called implicit differentiation. We still have to do it, but that's the process. You're just taking derivative on both sides. So on the left side, we have a sum, right? And because we have a sum, we can do them individually. So I'm taking derivative with respect to x of x squared. And then I'm going to take derivative with respect to x of y squared. And that will be equal to 0 because the derivative of 1 is 0. We already know that derivative of constant is always 0. Doesn't matter what you're differentiating with respect to, derivative of constant. That's one good thing in calculus. Doesn't matter what calculus level you ever get to. The derivative of a constant is always 0. You can't possibly have a rate of change if something is held constant, right? If you hold something still and then ask the question, how much is it moving? It's not moving, right? Derivative constant is always 0. All right, let's see if you understand this now. What is the derivative with respect to x of x squared?
2x.
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 2x, just like it was before. Now I'm going to do something even more though. You don't have to do this. I'm going to write 2x times dx dx. What I'm illustrating here is the chain rule. I've got something squared. The derivative of it is 2 comes out. That's something to the first power. And then I'm taking derivative of the inside x, and that's dx with respect to x, which is 1. Now, the reason I like to write that is because of the next one. Now I want the derivative of y squared with respect to x. So you're going to do power rule, right? 2y. But then you're multiplying times what?
dy dx.
dy dx. And then equals 0. Yay or nay there?
That's interesting.
Can you explain why you're multiplying by dy dx? Because I don't see like dy dx inside anywhere.
Okay, so we're trying to take the derivative of y squared, right, with respect to x. So do you see that you have something squared we're trying to take the derivative of?
Yeah.
Okay, so let's do the chain rule on that. The 2 would come out, right? And then you have that box thing to the first power. Well, what's the box thing?
The y.
Y. Okay, now times, now you're ready to take derivative of the box, right? What's in there? So you're taking the derivative of y, right? With respect to what variable though?
Oh, I think I see what you did now.
Yeah, I'm taking derivative of y, but with respect to x, so I put dy dx. And now I don't need the first power on the y, so that's why I wrote just 2y. Does that make more sense? Good, okay. Now, again, this piece here turns into a 1, so this is really 2x plus 2y dy dx equals 0. And check it out, what we are trying to solve for, dy dx, there it is. Aren't we trying to solve for that? Isn't that what we want to know? Can you isolate this on one side of the equation? Well, we can bring the 2x to the other side, right? Subtract it on both sides. And can we divide both sides by 2y?
Yeah,
How did you get rid of the dx over? You get rid of the one next to the 2x.
This right here,
Yeah.
that's 1. Because
Oh, I
it's,
wrote it wrong. I wrote it as dx over dy.
oh, okay, yeah. We were differentiating both sides with respect to x, so that's going to be the case through the whole differentiation, always be with respect to x. There it is. Here's what we're saying, everyone. If you take this curve and you want to know the slope of the tangent line, the standard old slope of the tangent line that we've been looking at, okay, y prime, it will always be negative x over y. That means you need to tell me, remember how I said just a second ago that if we're looking at a circle and I ask you to, hey, you know, go out to this x value and tell me the slope of the tangent line, you're not going to be able to because you don't know if I'm talking about that point or this point. This formula requires 2 things, doesn't it? It requires you give me both the x and the y. And so let's try something. Let's do this. Things start to get really cool here with a circle. We take the circle of radius 4, right? That's the equation we started with. What if we went 45 degrees? What can you tell me about the x and y coordinate here? If we're at 45 degrees, what can you, I don't need to know exactly what they are, but what can you tell me about their relationship to one another?
They should
they
be
should be
identical.
equal.
They
Yeah,
should be
They're
equal.
equal, right? They're equal. It's 45 degrees, right? They're equal. So if I were to go to 45 degrees and I ask you right now, hey, what's the slope of the tangent line there? You would put the x and the y in here, but they're the same number, aren't they?
yeah.
And so you get -1. And doesn't it look like the slope of that tangent line should be -1?
Yes.
Yeah, it is. What if you
Now-
went straight? What if you went straight up to this point right here? This is the point 0,4. What
Yeah.
should the slope of that tangent line be?
Just looking at that should be a 0.
It should be 0. Then does it work? Take the x coordinate and divide it by the y. Take the x and divide by y. What do you get? 0.
0.
Right? Same thing down here. Slope of the tangent line down here. You take the x coordinate, divide by the y. But the x coordinate is 0. So it's going to give you 0. What about here, though?
That's undefined.
That's undefined. Does our formula match that?
Yeah.
Take the x and divide it by y. Ah, you're dividing by 0. It's undefined. Vertical lines have a slope that's undefined. This formula gives you the slope of the tangent line on the circle at any point. All you have to do is supply me the point. If you supply me the point, I'll tell you exactly the slope of the tangent line there. All right. Let's do another one. We may as well do this one. Find y prime. And what I mean by that is dy dx. I'm going to give you a minute. I'm going to give you two minutes to see just how far you can go with this derivative. maybe 3 minutes. I've started working it out, but I'm going to stop here.
Could you move the x over so you get x squared plus cosine y equals y squared before you take the derivative?
Oh, yes, you're completely free to manipulate the equation however you want before you differentiate it, but there's no need to. I mean, it doesn't really save you anything or you know, since the whole idea is that we have a way of finding a derivative without having to solve for one of the variables, it really doesn't matter how they appear. But yes, you can. Okay, so I'm going to call on somebody. I'm going to start at the bottom of my screen here with Jasmine. Are you there, Jasmine? Oh, Jake, are you there?
Yeah,
Okay, are you following along?
I'm trying, but I'm pretty confused, to be honest.
Okay. Do you see what I have written?
Yeah, I have the same thing written down right now.
Okay, all right, so let's but do you understand what's written? Are you able to get to that on your own? Are you okay with that?
I'll be honest, it's pretty damn confusing. Like, I'm probably gonna need a fair look with it.
Okay. So all we're doing is we are taking the derivative on both sides of the equation with respect to x. The reason we're doing that is because we're asked for this, right? So I look at the denominator, that's dx, that tells me I need to differentiate both sides with respect to x. Then I'm going to, since this is addition, I'm going to do each one separately. So this is the derivative with respect to x of the first one, plus the derivative with respect to x of the second one. On the right side, same thing. We have an addition sign, so we can do them individually. And now we just have to just crank out what these four derivatives are. So Bethany, are you with me?
Yes, I'm here.
Okay, are you following up to here?
Yes.
Okay, I'm gonna give you a choice. There's 4 derivatives. You choose which one you want to do.
I'll go with the first one then. I said 3x squared.
3x squared, perfect, right? Now, you do not need this, but I am going to tack it on dx. And that again is because if you think about this like a chain rule, the 3 comes out, x squared, boom, times the derivative of the base, which is x with respect to x, which gives you the 1. Good.
Is it really necessary though to actually write out the dx?
No, it's not necessary. However, that depends on whether or not you're going to get the rest of it right. If you keep missing it on the other one that where it does matter, then I would suggest you do it everywhere. That way you truly know what's going on here. Like for the next derivative. Who wants to give me the next derivative?
Negative sign of y.
Daniel Patterson? I think I saw
Yes,
Daniel.
sir.
on mute
Negative.
first.
Negative sign of y.
Negative sign of y.
Do you have to multiply it also by dy dx?
Yeah, I was gonna say.
Okay, so Daniel.
Yeah.
You took the derivative of cosine, so everyone think chain rule, and this is to answer, I think, Jake's question. We have to be thinking chain rule all the time now, okay? Cosine of a box, the derivative of that, Daniel, is negative sine of the box. Totally agree with you. But then we have to think chain rule times, now you need to take derivative of the y with respect to x, and dy dx is not 1. Do you see that, Daniel? That piece has to be there. So Jake, to answer your question, do you have to put the dx? No, if you know it's 1, don't put it, but don't miss it here because here it's not 1. Does that make sense, everyone?
Yeah, because when those different variables, it's something that just can't go away like 1.
That's right. It just doesn't go away. In fact, we don't want it to go away because isn't dy dx what we're looking for? So it needs to show up somewhere, right? It needs to actually appear. If we never do the chain rule, it's never going to appear. Okay, so now we go equals. Now the other one, let's see. Vasily, how are you doing with this?
Hello.
How about this one? Derivative with respect to x of x.
That's 1.
I was asking Vasily.
Sorry.
Well, it's 1.
Yeah, but so you understand it's because this is x with respect to x. This is like dx. I'm not going to write 1. I'll write 1 on the next line, but that's what this is, dx, right? So that's 1.
Yeah, it's 1 multiplied with x.
Okay. Ricardo, how about this one?
2y dy dx,
2y dy dx.
or multiplied by dy dx.
Yep, 2y dy dx. I like the way that rolled off his tongue. It was just like a very natural thing. 2y dy dx, right? That's that should start. You should start seeing it that way. It's just like, okay, chain rule. 2 comes down, y to the first power. Now derivative of y with respect to x, dy dx. And there it is. There's our derivative. This is our implicit differentiation. That step is done. Now we have to go figure out what dy dx is, right? And I see it. It's here and it's here, right? That's where it is. So what I'm going to do now is some algebra. Everything that has dy dx in it, I'm going to choose to move it to one side of the equation. And I get to choose. I can move everything to the left or everything to the right. I think I'm going to move things to the right. By the way, this is 1 and that's 1, right? So let me do this. I'm going to take this right here and I'm going to move it to the right. I'm going to take this right here. So I'm going to move that one that way and then move this one to that side of the equation. So on the left side of the equation, I have 3x squared. And then I brought this 1 over. So now it's -1 equals. Now I took all of this to the other side with the 2y dy dx. And when I brought it to the right, it became a plus sine y dy dx. Now, why do you think I brought everything with dy dx to one side and everything that didn't to the other side? Why do you think I did that?
You're gonna factor out the dy dx, then
I'm gonna
divide it off
factor it out.
in order to
That's
isolate
right.
it.
Yep, I'm gonna factor it out. So I'm gonna pull a dy dx out of both terms on the right-hand side, which gives me 2y plus sine y. All right. Factor it from here and here, which leaves these two terms. And then the final step to get dy dx by itself is to just divide through by this.
I have a quick question.
Yes.
This is one of those also like stupid simple but just questions. So, and I moved it all over, to the other side. So I have the same answer, I guess you could say, but it's just, the signs are all switched. Is that like totally the same? Cool.
Is your dy dx positive or negative?
My dy dx is I believe it should be, yes, positive. It's just
What do you have? Tell me what you have.
dy dx equals 1 minus 3x squared divided by negative sine y minus 2y.
Yes.
I don't know.
Yes,
Okay.
that's right. When you say all the signs are different, I just want to make sure that, yes, that is correct what you said. Yeah, so if you chose to move everything to the left, then your answer might look a little different, but it should be algebraically equivalent. Yeah, so that's it. Do y'all notice something again about this derivative? In order to know what it is, you have to supply me with both an x and a y coordinate, right? Then I can tell you the slope of the tangent line. And that makes sense because the graph of that was this one, right? So if I want to know, let's say the slope of tangent line, right? Ooh, does it not let me? Huh. It doesn't track points on these. That's interesting. Okay. So if I wanted to know the slope of the tangent line, let's say here, I would have to know both the x and the y coordinate. And then once I knew the x and y coordinate, then I could actually plug it into that formula. If I wanted it down here, it would be a different x and a different y, wouldn't it? So it'd give me a different answer. I don't think I've ever graphed the derivative before. That's right, I'm not gonna do it right now. I have to, sorry. It's 3x squared minus 1 over y minus sine y. Is that it?
2y minus sine y.
2y minus sine y equals, yeah, you know
It's
what?
plus sine y, not
Yeah,
minus.
I don't think it's going to, it's not going to graph it because, well, yeah, this is the derivative. Let me, I'm going to have to make them equal to each other. Yeah, it's got some issues here, but I think you can see here that if you look at the slope of the tangent line here at 0, right? And do you see that the black graph has an x-intercept there? And then the slope of the tangent line here is 0, and it has x-intercept there, and it's also the same over here. Yeah, okay, I just did that for my own personal. I don't think I've ever graphed the derivative like that. All right, let's look at the last one. Okay, I'm going to work through this one because we have time constraints. Due to time constraints, I'm working this one. I want to find dy dx. All right, so I'm going to take the derivative with respect to x on the left side of the equation. And then I'm going to say the derivative with respect to x on the right side of the equation. I'm going to do the right side first. because the right side is easier than the left. And I'm actually, well, I don't want to cut it short here. I'm going to break it. I'll break it up into two pieces for you. All right, the derivative of 1 is 0. Minus, now the derivative of sine of y. Chain rule, right? Chain rule, think chain rule. It's cosine y times dy dx. The derivative of sine of something is cosine of it times the derivative of the thing inside, which is dy dx, which isn't 1. With me? Okay. Left side, we got some issues here. We're trying to take the derivative of cosine of something, right? Cosine of something. What is the derivative of cosine of something?
Negative sign of it.
Negative sign of that something, right? Negative sign of the something. But we're not done, right? Chain rule says now multiply that times the derivative of what's inside. That's a product rule inside, isn't it? It's x times y. It's x times y. And I'm needing to take the derivative of that with respect to x. I'm doing it on the side here. The derivative of that, according to the product rule, is the derivative of the first one times the second one plus the derivative of the second one times the first one. Do y'all see the product rule happening on the x times y that's in the cosine? What is dx dx?
Just 1.
1. So this is 1 times y plus here dy dx is just dy dx, right? Times x. That piece goes right here. Okay, I haven't shown you one like that before. That's the first one that's worked that way. We'll run through it again. I'm trying to take the derivative of cosine of something. Chain rule says, okay, well, that's negative sine of that something. But then I have to multiply times the derivative of what's in here, but that's a product between x and y. So I need to figure out what the derivative with respect to x is of the product. So I run the product rule. Derivative of the first one with respect to x times the second, plus derivative of the second one with respect to x times the first. And then I just crank those out, and that's what gets slapped in here. I see a dy dx here and here. I got to get it to one side of the equation. Are there any questions on how I got this? I need to get dy dx by itself on one side of the equation. Unfortunately, this dy dx is trapped in this parenthesis, right? It's trapped in here. So the only way to free it from this parenthesis is to actually distribute this through the parenthesis, which means my next line is going to look like this: negative y sine of xy. All I did there is multiplied y times this. And since I can't put the y inside because of the sign, I just slap it out in front of the sign. And when I do this times this, I'll get a minus. I'll have the x, I'll have the dy dx in front of the sign of xy again. So again, this right here can't go inside, so I just put it out in front. I changed the order. I hope that's okay. Put the x in front of the dy dx. You could have done it the other way. And then equals the other side, negative cosine y times dy dx. Now the dy dx are both this term here and this term here, right? That's where they are. So let's get them to one side. I think I'll move them to the left this time. So this one's going to go to the left, and that means I'm going to take this one that doesn't have dy dx and move it to the right. So my next line should be cosine y dy dx minus x dy dx sine xy equals y sine of xy. So that went to the right, so it made it positive. This went to the left, which made it positive also. So I put it in front of this. There's dy dx, factor it out. We're almost there. Last step is to divide through by all this ugly stuff. So dy dx will equal y sine of xy divided by cosine y minus x sine of xy, sine of x times y. There's your derivative. Questions on any of the algebra here? What happens if you miss that product rule? What if you look here and you take the derivative of this and instead of doing this, you tell me that the derivative of x times y, you tell me that that derivative is 1 times dy dx. Do you see what I just did? I took derivative of x with respect to x and got 1, and derivative of y with respect to x got dy dx. Do you see? This is like completely wrong, right? So there's a lot of things that you have to keep track of here. You have to make sure you're hitting it with the chain rule, right? Getting that, and then you have to make sure that you do the product rule there. Lots of room for error here. All right. We have 8 minutes still. There's one more thing I wanted to show you with this implicit differentiation. And that is something related yet unrelated. So I'm wondering if anyone here has ever seen this before.
Familiar from somewhere.
Equals nRT.
And chemistry.
Chemistry. Anyone know what that's called? No?
Isn't that like is that gas law or something? Okay, I can't remember.
The ideal gas law.
Oh, yeah.
So this is an equation that is used in chemistry that has to do with containers that hold things in them like gas. So if you take some sort of container or vessel, a sealed container, and then you put some sort of like gas or something in that, then this equation relates things together. It shows you how things relate to one another. So this right here is pressure. This is volume. This is temperature. I believe N is the number of moles. If you don't know what I'm talking about, it's a chemistry thing, don't worry about it. And this, I believe, is it Avogadro's number or is it another it might be another constant. I don't remember.
It was a constant.
Some constant. I don't know which one it is. Well, it's a constant, and this is also constant. So the lowercase letters here are constants. So these two together are just a number. All right. What this equation says is that if you were to, let's say, increase the temperature. So if you were to take the temperature and start increasing it, so maybe you start heating this up, right? You start heating up, you put some flame under here, right? You start heating this container up. Those are some good looking flames. I must say myself, a little burner, a little gas line in there. All right, start heating this thing up, right? If the temperature goes up, in order to maintain equality, what has to happen on the left side?
The pressure or volume have to go up.
One of those has to get bigger, right?
Yeah.
Well, if your container is sealed, right, and
Well, you can't.
can't change the volume, then your pressure's got to go up. Which is why when you heat things up and then, they can explode after a while because the pressure gets too high. This works the other way around. If you decrease the pressure, if you decrease the temperature, right, then the pressure goes down. Here's another way of looking at it. If you decrease the pressure, what should happen to the temperature?
It should go down.
It should go down. If you decrease the pressure, the temperature should go down. You may have experienced this before. If you've ever taken a soda or something, open it up, you hear it go, psh, right? That air that comes out is always just a little bit colder than it was when it was in there. As soon as the pressure is released, it becomes colder. Now, for any of you who know anything about air conditioners, we rely on this equation quite a bit. The basic way that an air conditioner works, and I'm getting very basic here, is that you have outside of your house, you have this thing that you probably seen those before. Outside your house, it's a fan, it's blowing, right? So in there is a pump, okay? There's a pump in there. And what it does is it takes Freon, okay? Freon is both a liquid and a gas, depending on its pressure and temperature. So it takes this pump, right? This pump takes this Freon and it pumps it through here, okay? And it pumps it around this unit. And the fan is blowing and it's pulling air over these coils and it's basically releasing the heat from the Freon. It's taking the heat and it's pushing it to the outside of the house. That Freon then goes through and gets condensed, means it gets put under high pressure. So the pump is creating very high pressure and this goes into your house. So you've got this Freon that goes up, wherever your air conditioner is up in your attic or something, this very high pressure. So P is very high on this Freon. And it goes through here and then there's this little tiny nozzle. And the Freon is under, like if I were to zoom in, here's the pipe, there's this tiny little hole. And all this Freon's in here and it's under very, very high pressure and it has to get through that little hole. And when it comes out the other side of that hole, there's no pressure. The pressure is released. So high pressure here, low pressure here. The entire system is sealed. So there's a fixed volume. And so what happens is that if the pressure drops, well, then on this side, the temperature has to go down too. So now you've got this really, really, really cold Freon that runs through coils in your attic. And then there's a fan there blowing your air from your house over those cold coils. And that's pulling the heat out of the air. Then that air gets blown back into your house. And that's your cold air. And then this Freon, which is now warm, has warmed up because it's been cooling off your air in your house, comes back outside. It's hot Freon at this point, goes through here, removes any other heat, and then it goes back through and it repeats the cycle. Gets put under high pressure again, sprayed out, drops in temperature, goes through again. It's just an endless cycle, right? So it's not free, right? You don't get this for free, right? What do you have to do in order for this to happen? You've got to run a pump, right? You've got to run that pump, that's power. You need to run the fan, and then you need to run the fan in here. So you got basically 2 fans and a pump to make cold air. But all it is using the PV equals nRT ideal gas law just over and over and over. All right, now why am I mentioning this? This is not an air conditioning class. This is not, it's not a chemistry class. It's because if we take this equation, I'm gonna run out of time. If we take this equation and I ask you this, to find dV dP. What I'm asking you is this. Can you tell me the little instantaneous rate of change in volume with respect to pressure? So if we change the pressure a little bit, how much will the volume change? Oh, does that make sense? That's what I'm asking. If we change pressure just a little bit, how much will the volume change? Well, the way to do this is to take this and differentiate both sides with respect to what?
DP.
P, right? D. So I'll go DP or D, DP, D, DP, and then over here, P times B, over here, N times R times T. I have to move fast because I'm out of time, which means I have negative 10 seconds left. All right, so here I go, real quick on the left-hand side. I'm going to take the derivative of this and I'm going to use the product rule, which means I'm going to take the derivative with respect to P of P times V plus the derivative with respect to P of V times P equals NR times derivative of T, derivative with respect to P of T. All right, so on the left, I took the derivative of this one with respect to P times this one, plus derivative of this one times this one. That's product rule. Equals, I ignored N and R. I just brought them for the ride because they're constants. Times the derivative of T with respect to P. So this is 1, right? That's 1, dP dP. So this is volume plus, this is dV dP times P equals NR, and then this one is dT dP. All right, now that's all I can do because I'm out of time, but there it is. That's what I'm looking for. I have it in an equation now. So I can now start talking about instantaneous rates of change in volume with respect to pressure. This, look, everyone, I know it's time to go, but this is like a profound thing. This will work for any equation, whether it be chemistry, physics, biology. You give me an equation, I have a way of actually talking about how if you change one thing here, how it will impact other things. For any equation, as long as I can differentiate implicitly, as long as I can apply the product rule, chain rule, whatever rules I need to apply, every equation you ever face in your life, you can always do this to. It's a major, major, I guess, advancement when it was discovered that you could do this. All right, we have to go. Your homework, man, I think you can at least try it. Yeah, go for it. I would say the first, thank you for hanging out here. Implicit. Yeah, at least up through 13. I mean, go for it, man. I mean, there's really nothing, you have the idea. Yeah, I mean, some of them are a little weird because you asked for the second derivative. So I think maybe 25, 26, 27, 29, maybe hold off on that. I'll show you an example of that next time. But I'd say for all these, man, go for it. Good luck. Do your homework. Chain rule and implicit, do it. Because next week we start what if you go ask any Cal 2 student what they hated in Cal 1, they're going to say related rates. They're going to say that was the hardest thing. It's word problems. Next week, we actually get to do something with this, word problems. All right. Enjoy your weekend.
Thank you, sir. You enjoy yours.
Thank you, you too.
Bye. Have a good weekend.
Bye.